So, guide to the calculus introduction of AP Physics. So, this first one, I give you a position function, and right away you notice it is a cubic. So, it is not a quadratic, so it is not constant acceleration. Thus, you will not be able to use the big three equations, right? Now, in the future, you have to recognize that on your own. Obviously, this is a calculus worksheet, so you know everything on here is going to be more calc-based, but right away when you see that position function, you see it's a non-quadratic, boom, you know right away it cannot be solved using the big three. You've got to use calculus. And so what we do is we end up using what they call the power rule. The power rule is just a rule that we use to take derivatives of polynomials, and this is very easy. So the power rule simply says we can take the derivative of each one of these separately. The derivative of t cubed is bring the power down, decrease the power by 1. The derivative of t cubed is 3t squared. The derivative of negative 6t squared is negative 12t. The derivative of negative 36t is negative 36. And that's just following the nice, easy power rule. And of all the derivative rules, it is the easiest. The derivative of 4 is 0. If you remember, 4 is really like 4 times t to the 0 power. Bringing that 0 down would decrease it. And you can also think about the derivative. Remember, the derivative is nothing more than the equation for the rate of change of something. The rate of change of 4, well, 4 is a constant, so the derivative of 4 should be 0. 36t, well, that's a line. The slope of 36t is just 36, so it shouldn't be shocking that the derivative of 36t is 36. And then if we want the acceleration, we know the definition of acceleration. Acceleration is the rate at which you change your velocity. So the derivative of velocity is acceleration. The derivative of 3t squared, again, follow the power rule, bring the power down, decrease the power by 1. The derivative of 3t squared is 6t. The derivative of negative 12t is negative 12. And now I have an equation for instantaneous velocity and instantaneous acceleration. All right, now we can answer some questions. When is the object moving left? Okay, well, the definition of moving left is when the velocity is negative. So I'm going to go back to kind of algebra 2. I'm going to look back at this velocity equation, and I want to know, when are you negative? Well, you could just graph it, and you could look for when is the velocity negative. Okay, go ahead and graph it if you wanted to, or you can factor it. And I did give you a pretty easy one. I factored out a 3, and that left me with t squared minus 4t minus 12, and then I looked at this, right? And I'm practicing using a sign chart, which we'll use a lot in calculus. And so the velocity is equal to 0 at negative 2, which is not in the domain. Remember, I did actually restrict this for only t greater than 0, right? We're only moving time forward. We're not going backwards in time. So I've just plotted 6, and I plotted the endpoint of 0. And so you can show that it's pretty easy when t is between 0 and 6. This is negative, right? Like, just pretend t is like 3. It's going to make this a positive. It's going to make this a negative, so the velocity is negative. And then the velocity is positive. So the question is, when is the object moving left? When is the velocity negative? Well, the velocity is negative at 0, which is why I used a bracket, all the way to 6. And then actually it stops at 6. So this is the interval when you're moving left. After that, you're moving from the right, 6, all the way to infinity. When is it moving fastest? Again, fastest is saying, when is saying at what time, and then we actually want to know what the speed is. And so for me, I just graphed speed. Reminder, speed is the magnitude of velocity. So I just graphed the absolute value. Remember, absolute value does mean magnitude. I graphed the absolute value of the velocity. Again, I just looked at this curve right here, and I just graphed it. And I looked when t is equal to 0. And again, I did graph the absolute value of it. And I figured out, hey, when are you the biggest? Well, at that moment, that little vertex there, that is the biggest the velocity ever gets. That's the biggest the speed ever gets. And that particular speed is exactly at 2, and it's got a magnitude of 48. So at 2 seconds, it happens to be going left, but it doesn't matter. We're looking at speed, and it's going 48 meters per second. Sorry that I didn't include the units there. Okay, find the average velocity over the 3 seconds. Again, when you get these questions, They get complicated unless you just go to the definition. We know what average velocity is. The definition of average velocity always for every situation known to man is delta x over delta t. If you want to know your average velocity over a time interval, tell me what'd you do and how long it took. So let's figure out where we are at 3 seconds, where we are at 0 seconds, and then divide by 3. That's what I did, and that's how long it took me. That's then on average what happened. So I plugged in 3 for time and 0 for time into my position equation and got negative 31 and 4. And it took me 3 seconds to do it. So then I know I must have gone negative 45 meters per second on average per second over those 3 meters. At what time or times does it pass through the origin? So the question is, what does it mean to pass through the origin? Well, that's similar. What does it mean to move left? Moving left is a velocity of negative. What does it mean for an object to pass through the origin? Well, the origin by definition is an x value of 0. So I went up to the x equation and I set it equal to 0 and I solved this for time. I happen to do it on my calculator, so I graphed this and I found the x-intercepts. There are your 2 x-intercepts. At those times, those are the times where the position is 0. Again, answer questions by going to the definition. What does it mean for an object to pass through the origin? That's an x value of 0. Okay, make x 0, solve for t. All right, now we're going to do the reverse. Again, this is like the reverse power rule, right? This is what we call antiderivatives or integrals. Now we need to increase the power by 1 and divide by the new power, which again is the exact opposite of bringing down the power and decreasing, right? We are multiplying and decreasing, and now we're dividing and increasing. So what I did is that I gave you the acceleration curve, and I gave you the initial, or I gave you some initial conditions. I didn't actually give you the initial position. I did give you the initial velocity, but I gave you information. And with that information, you can find those unknown quantities. So to find the velocity, I need to integrate or take the antiderivative of the acceleration, because we know those are inverse functions of each other. So I take 24t and I increase the power by 1 and then divide by the new power, and I get 12t squared. I increase the power by 1 and divide by the new power, and I get 6t, and then plus some v naught. I'm not sure what that is. We're like, oh, actually, look, it says right here, v of 0 is 10. That is telling you that the initial velocity is 10, so this must be 10, and now I can actually write the full-blown equation. Okay? Now, once I have the velocity equation, I then can find the position equation, because we know that if you accumulate velocity over time, well, that's the changing of a position. So I need to integrate the velocity to find position. So integrating 12t squared. Increase the power to a cube, and then divide by 3 gives you this. Increase this to a quadratic, divide by 2, gives you this. Increase this to a t, divide by 1, gives you this, plus some unknown quantity. We're not sure where we started. Again, just looking at the velocity curve does not tell you where you started. However, we can use this fact. We know x of 1 equals 6. Tells us that when t equals 1, we're at a position of 6. So just come down here and look at this equation and say, oh, all right, well, let's plug in 1 for t, and let's plug in 6 for x. And we know that's true, because we know when t equals 1, we're at an x value of 6. And so we know this and this and this and this, and the only thing we don't know is this guy. And that's the goal, to find it. And so if you just do some little algebra, we find out that x naught must be negative 11, and then I can come over here and write the full-blown equation. Position function must be then 4t cubed plus 3t squared plus 10t minus 11. Okay, these questions are the exact opposite of each other. This was position, take a derivative to find velocity, and a derivative to find acceleration. This is given acceleration, take an antiderivative to find a velocity, and an antiderivative to find position. Again, I usually say the word integral, where Mr. Gimrick usually says antiderivative, and they are the same, so no big deal either way. All right, now let's do some multiple choice bookwork questions. Get it maybe a little more challenging. So this is a position function. You can see it's a cubic. So again, can't use the big 3. We got to use calculus. And we want to know the maximum possible velocity, positive velocity attained. So what I did is I took the derivative and found the velocity, and then I graphed it. Or actually, in this case, I didn't graph it because it was just obvious that 4 is the maximum positive. That's a very easy quadratic, right? Right there. So 4 meters per second. This one's all about units, okay? So if you look at this, all of these are kind of crazy, but look at that equation. It's 2 times v times t minus 4 times x equals b times t squared, and you want to kind of know the units here. Okay, so what are the units of 4 times x? Well, 4 is a scalar, and x is in meters. So that term is in meters, and since you're adding and subtracting, everything has to be in meters. Think about that first one. 2 is a scalar, it's just a number. A velocity times time. A meter per second times a second gives you meters. T squared, so then what must be end up being? Well, that term has to be in meters. So then b must be meters per second squared. Meter per second squared times second squared gives you meters. And again, they all end up having to be meters because you're adding and subtracting. You can't add and subtract apples and oranges. Everything has to be apples, apples, apples. 15, I think this one is pretty easy. They give you the velocity curve, and they want the acceleration at t equals 2. Remember, the acceleration is just the derivative or the rate of change of velocity. So I took the derivative of this, bring down the power, decrease, bring down the power, decrease. So there's your acceleration curve, and I want to know the acceleration at 2. Well, I'm just plugging in 2 seconds into t and getting 10 meters per second squared. 33, all right, this is some velocity curve, and it's in the abstract, right? Some alpha, some beta, and some gamma. That's okay. We just know we want to find the displacement. We know the displacement is the accumulation of velocity during a time period. So all we have to do is do the power rule. So we just do the power rule in the abstract, right? Increase the power to a cube, divide by 3. Increase the power to a y squared, divide by 2. Increase the power to 1, divide by 1, and you get this guy. Okay, it's just the power rule. And then if we want the acceleration, well, the acceleration is the derivative or the rate of change of velocity. So I go back up to the velocity curve, and now I take a derivative of alpha t squared, and I get 2 alpha t plus beta. Again, decrease the power after bringing the power down by 1. All right, this is derivative. This is antiderivative. They're going in opposite directions in terms of the velocity. Accumulating velocity gives you position, or in this case, displacement. Taking the rate of change, the derivative of velocity, gives you the acceleration curve. All right, so the plane starts at rest, so v naught's equal to 0, and we got some crazy acceleration curve, right? Cannot do the big 3. We have to use calculus, and we know this is a fact. If you want to know the change of velocity, it's the area under the curve, which is the same thing as accumulating that acceleration over that time period. So if we integrate b or beta t squared, we get 1/3 beta t cubed. V naught was 0, so we can forget about it. And then all we got to do is plug in a beta, it's 1/90th, and then 30 seconds. So we're plugging in 30 seconds for time, 1/90th for beta, and we type that in our calculator, and of course we get 100. All right, 21. They gave us a position curve, and we want to know where is it located at 3 seconds. Oh, find the position of the particle, find its velocity, and find its acceleration, all at 3 seconds. All right, pretty straightforward. They gave you the position as a function of time. Just plug in 3 and get 2. Take the derivative of position to get velocity, plug in 3 seconds and get the velocity at 3 seconds. Take another derivative and get -2, and it's actually constant, so the acceleration is always -2, and you get this. Probably didn't even need to do this, considering you just can read off the information right here, because this is classic, right? This is a quadratic, so this is standard x naught v naught minus 1/2 at squared. You can see that -1 is really 1/2 of -2. Right, 38. There's a position function, and we want to find its position when it changes direction. Okay, so let's figure out, when does it change direction? Well, it changes direction when velocity goes from positive to negative or from negative to positive. So let's figure that out. Well, they start us out with the position equation. let's take a derivative to find velocity, and then let's figure out, well, at the beginning, this is positive, and then it goes to negative. We can figure out, basically, we're figuring out when the velocity is 0, right? That's when it's going to stop and then change direction. So at t equals 3/8, the object goes from moving to the right to moving to the left, right? At that moment, it's actually stopped. So then all we have to do is figure out where it's located at that time period, which means all we got to do is plug in 3/8 into t and figure out this value. That's where it's located when it changes direction. Again, it changes direction when the velocity changes sign, when the velocity is equal to 0. All right, next part, determine its velocity when it returns to the position it had at t equals 0. All right, well, at t equals 0, it's at a position of 2. Look, right there. X equals 2 when t equals 0. So when does x equal 2 again? Well, all I did was set this equation equal to 2. I want to know at what other time is t equal to 2. And I figure out x is equal to 2 at that time. So when t equals 3/4, it's back to where it started. And now I want to know its velocity at that moment. So then I'm going to take 3/4 time, and I'm going to take that value, and I'm going to plug it in to the velocity equation. Because I know at that moment is when it's back to where it started, and I want to know how fast it's moving at that moment. And it's actually moving at a -3 meters per second velocity. All right, last one. The height of the helicopter. All right, so number one, this height is a cubic function, which means this helicopter is not uniform, constant acceleration. This is a funky helicopter doing something crazy. However, it's pretty still easy. Here's the height. Let's take a derivative to find velocity. Okay, at 2 seconds, let's figure out how high it is and how fast it's moving. So plug 2 into t and figure out, all right, the helicopter is 24 meters in the air, and let's plug 2 into the velocity equation to figure out how fast it's moving. Now we're going to release. We're going to release the package. Now remember, the package is the mailbag. The mailbag is in the helicopter. The mailbag is moving up at 36 meters per second because so is the helicopter. Everything in the helicopter is moving at 36 meters per second. So when you take this mailbag, and you release it from the helicopter, you're not throwing it up or down, you're just releasing it. It is moving up with the helicopter at that exact same speed. And so we know that the mailbag is currently 24 meters in the air, moving at 36 meters per second up, and now it's going to be under the influence of gravity because you've dropped it, so it's no longer in the helicopter. So we're going to put a -1/2 gt squared, where g is the acceleration of gravity, specifically 9.8 meters per second squared. And all we want to do is figure out how long it takes to reach the ground. And so we want it to hit the ground. All we want to do is make y is equal to 0. And so we just graph this on our calculator, and it's going to go up and down. And when it crashes down, it's at a y value of 0, and we can find the time it takes to make that happen. Okay, this is probably my favorite one. And again, this is the idea of even relative velocity, that when you're in a car, you're moving as fast as the car. A ball is moving as fast as the car. And in this case, the mailbag is moving up. Now, the helicopter will continue to accelerate up, but when you release the mailbag, it is not going to instantly drop. It's moving up, and it's going to go up first, and then gravity slows it down and stops it, and then it's going to go and smash to the ground. And so we actually have to use this equation. Again, once it leaves the helicopter, then it's under standard position equation because it does have a constant acceleration due to gravity. Okay, hopefully this helped you out on all of these questions, and we continue to move forward now that we have both an algebra approach, if it happens to be constant acceleration, and a calculus approach, if that rate of change is non-constant. The only one thing I want to point out is, as a reminder, look at position. Cubic, quadratic, linear. That's always going to be that way. Normally, it's quadratic, linear, constant. So now it's cubic, quadratic, linear. Look at down here. Same thing. Acceleration was linear. Velocity became quadratic. Position became cubic. Look even down here at the helicopter one. cubic, velocity was quadratic. If I wanted to find the acceleration, it would have been 18t, linear. That will always be true and hopefully easy to kind of see those patterns.